Hello, everyone, and thank you, Grace, for the introduction. My name is Rick Paulino, and I am a technical specialist here with RheoSense, and I will be conducting the PowerPoint presentation as well as the live demo after the presentation. So I just have to say the PowerPoint presentation is running a little bit slow, so please have patience. So first I'd like to introduce our team. Grace is our marketing and sales specialist who set up this whole web demo for us. We also have Lulu, my counterpart, technical specialist, and me, Rick Paulino, another technical specialist with RheoSense. So now before I get into the m-VROC, I'd like to introduce you to RheoSense. RheoSense is a market leader in the biopharma industry. We specialize in viscometry measurement as well as fluid characterization. We are located in the San Francisco Bay Area in Silicon Valley, and we were established in 2001. So this is an outline that we'll be following today. I'll talk about the VROC technology that powers the m-VROC, as well as an introduction to the m-VROC. I'll also cover applications that, for example, biopharma, as well as inks and biofluids. I'll also go over the ease of use of the instrument, and I will also cover the RheoSense product line. And once the PowerPoint presentation is over, then we will have our live demonstration. So now I will speak to you about the VROC technology. So what is VROC technology? VROC stands for Viscometer Rheometer on a chip. And it is basically a hybridization of microfluidics and MEMS technology. The microfluidics allows for small sample volume, and the MEMS technology allows for absolute viscosity, as well as the ability to provide a wide dynamic range in shear rates, as well as temperature sweeps. It is also fast and superior in repeatability. Now to get into a little bit more detail about mVROC technology, the mVROC technology is based on an elegantly simple design. You basically have a microfluidic channel where sensors are embedded into the channel. The fluid flows into the channel, and as the fluid passes over the sensor array, there is a pressure drop. And this pressure drop is proportional to shear stress. We use a variation of the Hagen-Pasulli equation where viscosity is equal to shear stress over shear rate. Now we get shear rate by knowing the exact dimensions of the microfluidic channel. Couple that with a positive displacement pump where we know the exact flow rate, and those two parameters give us shear rate. Now shear stress over shear rate will now give us the absolute viscosity of your sample. Now the m-VROC is very flexible. It has a wide dynamic shear rate as well as a wide temperature range, all the way up to 105 degrees with certain options. Also, it's very accurate, 2% accuracy, as well as a very repeatable, 0.5% of full scale. It also has the ability to measure non-Newtonian, as well as temperature sweeps and rate sweeps. And if I forgot to mention, minimum sample volume, only 50 microliters. So what are the applications? Right now, I will talk about 4: biopharma, viscosity fingerprinting. This is the ability to fully characterize your sample by use of shear rate sweeps, temperature sweeps, as well as the ability to fully characterize the uniqueness of your samples. Also has the ability to perform injectability studies. This is very important, particularly when high shear rates are required. In the needle, high shear rates typically, or they will dictate the injection force of your proteins. Also, for batteries, knowing the viscosity of your solvent is critical to ion conductivity. As well as inks, the m-VROC system is a closed system. So for volatile 3D ink printing, this is an ideal system. You also have the ability to fully characterize your inks for optimization of formulation. And in biofluids, you can use blood viscosity as a tool for medical diagnosis. So now that I've spoken about mVROC technology and applications, I'll talk about the ease of use, followed by the RheoSense product line. So the m-VROC is controlled with your laptop, and data can be seen in real time. There's no need to wait for your experiment to be done to actually analyze your data. It's also exported to Excel and PDF, and the interface is, and we've designed the interface to be intuitive. So these are actual screenshots of the m-VROC control software. So if you follow my pointer, it's a very simple procedure. You basically input your sample. In this case, it's IPA. You put the estimated viscosity. You also put the sample volume in the syringe. And once that is inputted, in the run parameters, it will give you very useful information. For example, it will tell you what the estimated minimum shear rate will be, as well as the estimated maximum shear rate. And you can use those run parameters to input your run data. For example, in this example, we have a shear rate of 3,000 per second. We're going to run it in auto mode for 30 seconds, and also we'll do a pause time of 6 seconds. In this next, once you've inputted your parameters, it's basically hitting start, and once start is pressed, then the m-VROC will begin to measure your data. And so two graphs that I'd like to point out are this viscosity graph, which will actually give you the viscosity in real time. It'll give you the viscosity at the moment as well as the average. And also another helpful feature is the percent full scale. We suggest running the experiment between 5 and 95% of the scale of the chip. And the chips, we have a variety of chips that have the ability to measure a wide range of viscosity as well as going from low to high shear rates up to 1.8 million inverse seconds. There's also a optional temperature control, and this temperature control is also very, very easy to use. You basically input your temperature setting, and the thermocube, the water bath, will automatically adjust to the temperature that you've set with a minimum stability of 0.15 C. When the sample has been completed, you also have a very useful results summary, which will tell you, for example, the temperature of the sample, the shear rates, as well as the apparent and true viscosity of your sample. The apparent and true viscosity come in handy, particularly when you are measuring non-Newtonian fluids. The true viscosity for non-Newtonian fluids will be based on the Weissenberg-Rabinowitch correction equation. Fast setup and fast cleaning are also a hallmark of the m-VROC. The m-VROC is very easy to use, and it's very simple to clean. You basically clean the sample just the same way as you run a sample. You use a miscible fluid, and you basically just run 2 to 3 mLs of the cleaning fluid into your chip, and it's cleaned up and it's ready to go for another run. So now I'd like to introduce you to the RheoSense product line. I've gone over the m-VROC. However, the m-VROC has two variations. We have the HTS here in red, and the HTS is for our high temperature sample requirement. That will go up to 105 degrees. We also have the m-VROC here in this aquamarine, and the m-VROC is our extensional viscosity viscometer. We also have our microvis, which is our portable unit, and the microvis has the added function of temperature control, much like the m-VROC unit. And last but not least, we have the m-VROC Initium. This is our automated high throughput viscometer. So that is the end of my PowerPoint presentation, and now we will go into the live demo, and I will demonstrate to you the ease of use as well as the chip selections for a variety of viscosity ranges, as well as syringe selections for high shear rate applications. Hello everyone, we're back. So this is the m-VROC unit, and the m-VROC, as I mentioned earlier, has the capability of testing a wide range of viscosities, as well as the ability to perform at high shear rates. So I guess I'll start off by showing you one of the chips. So this is an actual chip that we have. It's the microfluidics is contained inside this housing, and a syringe with your sample goes and connects right into the m-VROC chip. Now I've got it set up here where I have a chip that's already set up, and I have a 500 ml syringe, and what I'll do is I will run IPA, so you can see how easy it is to run your sample. So the first thing you do is you load your sample. You want to make sure that you get air bubbles out. And once I'm confident that I've got the air bubbles out, then I actually attach it onto the chip. I move the block, which will push the syringe plunger, opening up the chip, locking down the syringe jacket, and within about 30 seconds, I am ready to run my sample. So now I'm going to switch over to another screen, and this is the control software for the m-VROC. And what I will do is I will enter my sample, estimated viscosity. We're going to let's put 2.2. Sample volume, I have approximately 400 microliters. I also want to make sure I have the correct syringe selection. We can go all the way up to 10 mLs. So now, once I've inputted the measurement parameters, the run parameters will give me an estimation of my minimum rate as well as my maximum rate, and this is what I could use as a guide for my measurement. So we're going to start off by going 100, and I will set it to automatic, and that will give me my measurement time as well as my pause time. We also have the added function of generating a rate sweep. So in this tab, Generate Rate Sweep, we could set it up to run linearly. We can run it either rising or falling. We can run it as full scale or rate bound. So what I will do is I will clear this and we'll go ahead and run a rate sweep. We'll set this at 100 microliters. Actually, we'll go 20 microliters starting all the way up to 400. I hit append, and all my measurements are automatically populated here in the measurement parameter entry. Once I'm happy with my measurement data, I hit start. Also, another nice feature is the m-VROC software tells you how much your total volume measurement is. So I have about 120 total volume. So now I just press run or start, and we let the m-VROC do the work. So once the pump is configured and the baseline is measured, the m-VROC will begin to measure the viscosity of my sample. So as I mentioned earlier, the measurements are done in real time, and you can see the actual measurement of the IPA in the viscosity diagram. So now we've finished with segment 1, we're moving on to segment 2. I'd also like to point out how quickly the m-VROC goes through the rate sweep. So now I've completed my rate sweep, and at this point you want to save your data, and the data will be saved in a file of your choosing. We also have the results summary that I had mentioned earlier, and that's in this tab where you have the apparent viscosity. And in this case, because IPA is Newtonian, actually let me make a correction here. I had it on non-Newtonian setting, but we could also change it to Newtonian setting. And the results summary should reflect that here, where the apparent viscosity will be the same as true viscosity, which would be different from a non-Newtonian fluid. The true viscosity would have the Weisenberg-Rabinovich correction. Now, one thing also for repeatability, we suggest that you do 3 repeats. And so what I could do is I'm going to just change this, and we'll run it one more time, just to show how easy it is to make these corrections. Okay. Run it one more time. We'll do another 6 measurements. So earlier I was speaking about non-Newtonian. We also suggest that you do at least 3 measurements for repeatability. And there you have it, complete. And here are the results summary. Also, if you were using temperature, you would set the temperature, your desired temperature here. I don't have it set up, so it's not something that I could set at the moment. However, if you had the optional temperature control, this is the tab that you would set your temperature, and the m-VROC and the thermocube would automatically reach that temperature and maintain stability. So that is it for the web demonstration. And if you have any questions, we'd be very happy to answer them now.